In this presentation, we're going to talk about microcode and a simple computer architecture. Microcode is a set of instructions at the lowest level. It is closest to the hardware. Any higher level instruction, even an assembly or machine language instruction, must be converted to this lowest level. And in that conversion, a single instruction at that higher level, the machine language, a kind of very low level of programming, but still higher than microcode. A simple machine language instruction like load accumulator A, put some number in a particular place, consists of several microcode instructions. So where is this microcode? Where are these instructions stored? They used to be literally in the wiring. You would plug in wires, and hence the term hardwired. Now it will be stored in ROM, read-only memory. If it is put in EEPROM, electrically erasable programmable read-only memory, then it can be changed, and you would call this microprogramming. But this is done on a very rare occasion. And this code is sometimes known as firmware. So that would be intermediate between software, which is in memory and easy to change, and hardware, which is the sort of physical stuff and hard to change without sort of getting a new computer. So here's the relationship between machine language and microcode. Machine language is in RAM. It's software. It's easily changed, and it's the lowest level of software. It's one level above the microcode. The microcode is in ROM. It's hard to change. It's firmware. But the microcode is stored at an address in ROM. Remember that ROM is an addressable scheme of memory. It's just that one only reads it, or one very rarely writes it, so it's read-only or nearly only read. So the machine language is just a set of numbers, and basically those numbers are microcode or ROM addresses. They're the ROM addresses of the microcode. So the machine language just tells you where to go in ROM to execute what microcode you want to do. Okay, now let's head in the other direction. There is a mnemonic version of machine language. So instead of just some crazy string of numbers, which is an address in ROM, which makes no sense, we start to sort of describe mnemonically what the instruction does, and that will give us assembly language. So what do we mean when we say assembly is a mnemonic? Well, a mnemonic is a memory device, something to help you remember something. And so machine language is very difficult to remember. It's just long strings of ones and zeros that happen to be an address, and so there's no making any sense of it, no way for your mind to sort of grasp hold of it. But assembly is then more of a mini description of what the instruction does, and your brain, once you get into the mode of thinking of assembly, will remember such things. And then there will be some way of converting from the sort of simple thing that you can remember to the long string of ones and zeros address, and that will be the job of the assembler. So the programs that you might have written are typically high-level programs, and they must be gotten down to the assembly machine language level, and that's typically done by, say, a compiler. And then if you end up at some assembly level, then that has to be taken down a level to the machine language, and that is done by an assembler. And each processor is going to have its own unique machine language. And so then all the code that you have is going to have to be sort of rewritten, or if it's a high enough language that they all share, at least recompiled, so then it can be run on the different processors, on different hardware. Now, families of processor, everything say in the Intel family, will have a lot of common machine language instructions, and this will give them some backward compatibility to prevent some of these problems. Next, we want to start considering about putting all the little pieces that make up a simple computer into a little simple design. And the computer is going to have what we call a bus architecture. So all these different pieces of the computer need to communicate with each other, need to share data, send it back and forth. And so a bus is basically a set of wires in which you can send data. And when you call it a bus, it is implied that it is shared, that there are many possible sources of the data that is going to be traveling on the bus. And there are many possible destinations that the bus can reach. So it is a shared pathway for data. Another place that one talks about buses in networks of computers. So a sort of small subnetwork of computers will be connected by a bus, and then when you send information from one computer to another, it is put on the bus. So this schematic shows our little simple design, our architecture. And we're going to talk about the pieces sort of either individually or in small groups. But let's here, when we're looking at the overall design, take a few things into account. There's a channel running through the middle called the bus, which is how things are going to communicate with other pieces. And so we have these arrows. And so if an arrow points to the bus, that means that that device can put its information onto the bus. If there's a arrow pointing from the bus, that means that that device can take information from the bus. Some devices have both directions, so they can take information from the bus and put information on the bus. Some communication is not on the bus, so some of the arrows are from one device directly to another device and not on the bus. So some things, many things go by the bus, but not everything goes by the bus. And now we'll start to talk about the sort of individual pieces. So our computer is pretty useless to us unless we can input some data and input some instructions. So one at the top, we're starting with a keyboard encoder. So we're assuming that some of our input is going to come from a keyboard. And so that is going to take keyboard information and prepare it to be sent into the computer. And then there is an input port, and this is a place where data sort of can be held, sort of buffered, because the processor is sort of running and doing its thing, and we don't know when the outside world is going to try and communicate with the processor, and if the processor can deal with the data at the split second it's coming in. So it sort of gets put into the input port until the processor says, I'm ready to look at it. And that's what input port 1 and input port 2 are for. And we're just sort of generically saying there's a keyboard 1, and then there's some other type of data, some non-keyboard data, whatever that might be. In order to be a computer, it must be programmable. Therefore, we're going to write and execute code. And we know that our code that we write at some high level gets translated and compiled and so on down ultimately to machine language code. And then that is placed in memory. But also in memory is the data that we want our instructions to act upon. So in memory are our instructions and the data we want to act on. And so we're sort of jumping all around in memory. Well, memory is RAM, it's random access, and so we can jump all around in memory. That is fine. Memory can handle that. That's how it was built. But our normal progression through a program is linear. It's from instruction 1 to instruction 2 to instruction 3, and those are typically stored sort of in a sequence in memory. But in the meantime, to execute an instruction, we're jumping around and getting data. So we need a way to remind us where the next line of code is if we've jumped around and done some data things in the meantime. That's the job of the program counter. So we know what a counter does. A counter is something that holds a value but can also increment. So it will hold the value of the next instruction, and then when we go and get that instruction, we will tell it to increment, and then it can sort of move on. So that's why it's referred to as a counter. The design in the architecture shows a two-headed arrow, so that means that the program counter can give up its information to the bus, but it can also get information from the bus. Well, our normal progress through code is linear, but you all have coded at some point in your life, and you know that there are ifs and loops and subroutines, and so sometimes we do some jumping around. Sometimes we have to say that the next instruction isn't the next one in memory, but someplace else, and so we need to be able to change the value of the program counter, and hence the double-headed arrow. As we said, our instructions and our data are stored in memory in RAM, and RAM is random access memory, so that we can jump around from instruction to data back to instruction and so on. So we need an address, and so that is the purpose of the memory address register shown above the memory, and that it supplies the address. So when we decide we want to read memory, we put the address that we want to read into the memory address register. It may get its value from the program counter that we just talked about, but it may get its address from someplace else. If it's data rather than an instruction, it will be getting its data from someplace else. So the memory address register tells us where we're going to read data, what address we're going to use. Then in memory, we're going to sort of point to that address and get the value, and we will move that value into the register that is shown below memory, the memory data register, and it is going to sort of hold that value from memory until we do something with it. So that is by the connection between memory and MDR, and the connection between MDR and the bus are both bidirectional, and that is so that we can both read from and write to memory. Now the address is one directional, so the memory address register is just told what to do. Here's the address we want to do something, and it tells that address to RAM. So those are one directional arrows, but the data involves two directional arrows so that we can both read and write. So our code was in memory, and it involved instructions and data, and when we want to perform an instruction, execute an instruction, we will take that code from memory and put it into the instruction register, the IR. And so that tells us it holds the instruction that we are currently executing. So a given line of assembly or machine language is going to require several microcode instructions. So we need a place to hold the instruction sort of until it is complete. So that is the job of the instruction register. It's a bidirectional arrow because sometimes the instruction also involves some data. Sometimes it says add 5, and then we have to deal with the data. So that data portion of the instruction may need to be sent back out. So that's why it's a bidirectional arrow. There's a single directional arrow to control. That is the ROM. That is what knows how to execute the instruction. That's where the microcode actually is. Next is the controller sequencer. It is here in the controller sequencer. That is the ROM. It is where the microcode lies. This is where the ability to do for the devices, the hardware to do anything lies. And so it executes the program at this lowest level, but it's a firmware level. And so all of our devices all around the computer, they have certain abilities, certain things they've been designed to do. And then they need to be told sort of exactly what action to perform and when to perform it. And so each of the devices has control pins, and so the controller connects to these control pins. That's not shown in the schematic. So it looks like the controller sort of this dead end, this thing just hanging on, but quite the opposite. It's in control of everything, so it connects to everything and controls them. And again, it is the ROM. It is where these microcode instructions lie. So now the assembly level, the machine language, is a bunch of numbers, and that code was sent, and that was software code. That's the lowest level of software. That was sent to our instruction register. And basically, it's sort of serving as an address of the microcode instruction that corresponds to the machine level instruction. So more or less, the instruction register is sort of a ROM address register. So it serves a similar purpose to the memory address register that works with RAM, but this one's working with ROM. But since what it holds is an instruction, we're calling it the instruction register. Now we've moved to the other side of the bus at the top and are working our way down. So we have the accumulator and the ALU. So the ALU, the arithmetic logic unit, this is where we're going to perform our arithmetic and our logic. This is where data finally sort of changes and becomes other data. So like our adder or adder subtractor or multiplier, shift registers that are doing some kind of calculation, they would all lie here in the ALU. Now we need to do sort of arithmetic or logic, we need some data to act upon, and so the accumulator shown above the ALU is the sort of principal register associated with the ALU that is sort of the main area, the sort of first scratch area for us to get data to act on. So it's the first place where we look to get data to do arithmetic for. It's the first place where we will store our answers. It's just the principal register connected to the ALU. The flag is an output of the ALU, which is sort of distinct possibly from the answer to the arithmetic. So think of the carry in addition. So we perform an addition, we'll get a sum. We might put the sum of the answer back in the accumulator. But if that addition causes an overflow, then that information of the overflow might be put over into the flag region. Another thing that might be in the flag is the result of a logical comparison. So you might have a number in the accumulator and then another number down there in the temp that we haven't talked about yet, but it's the sort of secondary register associated with the ALU. And we might compare them, and so we don't want to change our data in either one, but we want the result of this logical comparison, and again, that could be put into the flag. Temp and B and C are additional registers to be used with the ALU. If the accumulator A is the principal, then temp will be the secondary. So it's directly connected to the ALU. It's the other piece of information that you might be adding or multiplying or what have you. Its distinction is that typically the answer might also be put into the accumulator. So it is used sort of less often than the accumulator. The accumulator is the principal, the temp is the next one, and B and C are there for sort of additional usage. And so to put data there temporarily. So it's easier to put data into a register than to put it all the way back over into memory, because with memory you're going to have to deal with the address register, the data register, and all that. So it's a multi-step process to deal with memory. So if you're doing some calculation and you have some answer and you need to sort of do something else for a minute and then come back to the answer, you might put it in B and C. Just as with the input ports with which we started, the computer's pretty useless if we can't get things in, and the computer's pretty useless if we can't get things out, so we need an output port. Now we don't want the outside world is slow and compared to our internal computer world, so these output ports include sort of registers, buffers, places to hold the information. So one of them is connected to some form of a display, output 3, and so we need it to be sort of held there. If the display displayed it for as quickly as the processor processed it, we would never sort of see it. Our eye can't take in the information that fast. And then we have a second output port, just sort of in principle that we might want to send things out other than to display, for instance, to storage.